Hello everyone. So in this tutorial, we're going to show you a minimalist RAG or Retrieval Augmented Generation example using Llama Index. So just to remind everyone, RAG basically adds your data to LLMs. So it makes it much more accurate by adding your data or external data to LLMs. So for example, ChatGPT, if you notice, sometimes it says like searching on Bing. It adds Bing's data. So LLMs, they don't have like unlimited memory. Basically, they're only learned up until a certain amount of time. They're only trained up until a certain amount of time. So they don't have access to like your data or to current events. So if you add that access, they give you much more accurate and better and more relevant answers. So that's why RAGs are like crucial. So Llama Index is, according to their website, the leading data framework for building LM applications. So it's like a very, very cool framework. There's tons of things you can do with this RAG stuff. And I'll show you more about it in other videos. This video is more of going to be like a simple basics video to really understand the concepts. But later we'll get to like much more complicated concepts with much more data, with data from various sources and that sort of thing. And also I'll show you how to do this AI trading bot where I showed you this little snippet in my other video. Okay, so first, by the way, Llama Index has some pretty good tutorial starter examples. And they have like a tutorial for OpenAI models, which they're the default models, use OpenAI, and for local models where you can use models on your own computer. And also they have like a high level concepts I highly recommend. This is really good stuff. So I highly recommend that. Anyways, of course, if you like my video, please like and subscribe. I really appreciate it. It helps a ton. Okay, so how does RAG work? So basically what happens is you have all your documents and you index your documents. When you ask a query, it's much more easier to find the relevant documents that help you get the answer. So how does this work? Okay, so like you can think of indexing as just any way to retrieve your data in a very efficient and smart way. So like in databases, like in SQL, you have like you can have indexes on date columns. So you can say if date greater than May 26th, then do this. And then your data is like stored in a smart way where you can easily retrieve things greater than May 26th. In our case, because we're working with these LLMs, we're storing things in embeddings. So embeddings are basically vector representations of your data where point and space are semantically meaningful. So like, of course, like similar documents are closer in space to each other than dissimilar documents. Okay, so the first thing in this RAG system is you index. You index your documents. Technically in Llama Index it's nodes, but I'll talk about that in a second. So you index your documents, and then what happens is you have a query. And the query, it's a query, you index your documents. So that means in the case of a vector index, you have embeddings for these documents, right? The query is also embedded. And then basically you go in a query and you find the k most similar documents to that query. So once you have the k most similar documents to that query, then that's the retrieval process. You shove that along with the query into the LLM and you get a response. So just to say that again, the retrieval is the k most similar documents. In the case of Llama Index, it's the k most similar nodes. Nodes are basically like further splits of documents, chunks of documents. So you find the k most similar nodes and plus your query, those two together, so the three most similar nodes and your query go into the LLM prompt, and that LLM prompt gives you your answer or your response. So just to show you the concept of nodes again, for Llama Index is you have a document, the document is split into these chunks, and you have an embedding vector for each of these nodes. The query has an embedding vector, And based on that, you find the k most similar embedding vectors to the query vector. Let's say k equals 2. You take the 2, that plus those two nodes plus the query, give you the response. Okay, so usually, by the way, the measure for distance or similarity for vector store indexes, like these embedding things, is the cosine similarity. So the cosine similarity basically is a way to measure the distance between these embedding vectors. And just I want to touch on an important thing that I won't cover much in this video, but metadata is extremely important. So like we can find documents closest to our query, but sometimes they're not relevant with respect to what we want. Say we only want, say like what is the news, Tesla news in the last 24 hours. So if you find the most similar documents to that, and you get things from like a month ago, it's not relevant. So that's where these metadata indices come in. So like in our case, metadata can be tickers, news source like Reuters, Bloomberg, all that sort of thing, and time published. So basically, these metadata indices can also be filtered, and we'll talk about that in future videos. But I just thought, because some tutorials ignore that, that's important to say that there are these metadata filters, and they're very helpful. Okay, so so let's get started. So first thing we need to do is we need to do pip install Llama Index. Okay, so once that's installed, what you need is, okay, so you can either use local embedding models or and local LLMs, but the default is to use OpenAI's both embedding model and LLM. But there's a settings parameter. I'll show you at the end how to change that. But remember, to get the OpenAI API key, which you're going to need is you go to this link. I don't know why it always tells me to sign up, but you can sign up. Continue with Google. Okay, so you have the settings, and you go to your profile, and you have user API keys. You get an API key, you copy and paste it into your secrets thing. And of course, one of my one of the nice people commenting said, you shouldn't use Chrome's autosave thing, so don't do it. So, but you copy and paste the key here. And then once you copy and paste the key, you can access it by name. So here it's OpenAI key, I called it. And then I can do like user data.get OpenAI key. And I set the environment variable of OpenAI API key to that because that's the default it takes. So watch this. Okay, so I grant access to that. Okay, so let's first load our data set with pandas. This data set is available on GitHub, so you can just run it as is. Okay, so it's only 5. How's it only 5 documents? I thought I had way more. What did I do? I thought I had like a lot more. It's weird. Okay. Anyways, the content we're gonna use is the content. We're not gonna use the headline, but just to show you how the content looks, you can do this HTML df.iloc0. You can see like an example of content. What is it called? df.content.iloc0. Let's do that. So like you can see an example of content. It talks about like future fund manager Gary Black. I'm a big fan of his, even though he's not always saying good things about Tesla. But like it even shows this tweet, which is pretty cool, this HTML thing. So this is like basically our document. Oops, sorry. Okay, so this is our document, and the other columns can be metadata filters, like author, headline is not really a metadata filter, but like symbol, updated, created at, updated at, that sort of thing. Updated at is very important if you're doing predictions. You don't want to like use future data in your model, for example, if you want to predict prices or something. Okay, so now let's talk about the steps. So step 1 is you have to get your data into like some sort of database, or in our case, we're just gonna like show you how to get it in general to your RAG system. So there are so many advanced data connectors. Like there's a Slack reader you can read from Slack, which is kind of creepy if you have a big organization and they can like search your Slack stuff. and it can give you the smartest. Actually, it's very smart. Actually, Discord, it can be very interesting because there can be like breaking news people post on Discord, and you can get like the latest and greatest, um, news relevant to certain stocks. Because Twitter API now is way too expensive, so maybe Discord can be cheaper. And they have so many connectors. You can look at this link. They have like so many connectors. They have Google Docs. They have like SQL. They look at all these things in their Panda CV. They have so many things. Anyways, but we're not going to use the connectors here because I do want to illustrate the concepts from scratch. So we're going to show you like step by step how to create these documents, the text in the documents because the text is the most important thing. And I'll show you also how to add this metadata information because later it's going to be useful for metadata filters. So basically each document we want in this form, the text equals text and metadata equals some dictionary of metadata. Okay, so let's do something like that. So I need the vector store index here, but whatever. So let's do documents. Let's just initialize the empty list and then let's do for index row in df.iterows. So let's iterate over our documents. Isn't that cool? The collab AI gives you like an auto complete, even though it did it wrong from what I want. But anyways, so just to remind you guys, when you iterate over a data frame, if you print, you can print like row, you get actually a series. So let me show you. You can do break. Let me just show you how this looks. I can do print index and then print row. Let me show you how this works. So the index is your index and the row is a series. I just want to show you guys how this looks. This is oh, I did row.content, sorry. Index is just your index and row.content is your actual content. Is a series. So you can actually create from, because remember we're going to need a dictionary for the metadata. So for the text, we can just do we can do row content. That will be text equals row content, and for the metadata dict, we can do. Let's just say we want the author and the created at and nothing else. So we can actually do something like this. We can make a row dict, basically transform the series into a dict by doing row dot to dict, and then you can do key value for key value in row dict dot items. Look, the auto complete didn't do what I want, but so then I'll do if k in, let's do created at. So we're going to only take the created at and author for our metadata. So this is going to be our metadata dict, right? So then we can do documents.append, document text equals text, metadata equals metadata dict. Okay, so this is, each document has this form. Okay, so now I'll just do, after this, I'll just do length of documents just to see length documents. It's going to be 11 documents. Weird. Didn't I just have 4 here? Oh, because I did that head. Head. Okay. The reason I had 4 is I did that head. Okay. So so I have 11, and I didn't need to print this out every time. You know, we'll just keep it anyway. So I have length of documents 11. So remember I said like the atomic unit that's used for finding the k nearest things is actually nodes and not documents. So nodes are basically chunks of your documents. So you're gonna need this like some node parser to split your documents into nodes. So the one that's used like as a default for the higher level APIs is sentence splitter. So let me show you how to do that. So you can do parser equals sentence splitter, and let's do there's a chunk size. That means you split every 512 tokens, and then there's chunk overlap. So chunk overlap basically means you're not just splitting with disjoint sets. You have like some overlap of like, let's say 64 in common between the two. And then when you do that, you get you get the nodes. Sorry, I wrote chunk overlap twice. Chunk size here. Chunk size. Chunky. So I got nodes, and then let's just print length of nodes at the end just to show you guys. So length of nodes, split documents. Oh, sorry. See, the auto AI trips you up because it recommended that, but it was wrong. So parser.get nodes from node document documents. So you get length is 34 nodes. Okay. So now remember from the nodes, so like here, this thing, I wrote documents, but really for Llama Index, it's from the nodes. You have to index these nodes into vector index. So that's where you do the embeddings for each node. So let's do that here. Okay, so how are we going to do that here? So we're going to do this like this. Index equals vector store index nodes, right? And let's look at the length of the index. Okay, sorry. Index, we can view the embeddings. Because remember, I told you this is where like it indexes things. So when it indexes things, it creates embeddings. So like you can do index dot vector store dot embed dot data. See the auto AI thing is not good with this library. Embedding dict dot values. Okay, so you get the values, and this shows you basically like the embeddings. It'll be like a dictionary from each node ID to an embedding. So let's you can't it's so let's do values. So this okay, so okay, let's first let's get the length of this. This should be we should have one for each node, right? So it should be 34. Okay. So 34 is 34. Okay, and then let me show you an example of like the first one. So the first one, if I do dot value 0, I'm gonna get oh, it's not subscribable. Okay, sorry. So I can do like this. I can do like this. I can get the first example. So you see, I have it's gonna be a mapping from the node ID. Oh, sorry, it's actually the value. Okay. I thought we had some sort of node ID. Oh, it's the values. Okay, but if I can get the key for this too. Assume I can do. Yeah, you should probably do next iter. That's probably the better way to do it. Let me actually do it properly. Dict. I'll do like something like a next iter, like this. And then I'll do key node ID embedding vector equals like that. Next iter is node ID. Forget what I'm doing. Sorry guys, I tripped myself up. So you have this embedding dict. And what is this embedding dict? Let me just remind myself. So type of this. So it's a type dict. Okay, so what are the keys? Keys. So, oh, the keys, yeah, this is exactly what I thought it was. You have the keys is here. These are the node IDs, and the values are the values. That's what I thought. Okay, so that's weird. Okay, so let me just show you an example. Let's look at the first. So the keys are the node IDs, and the values are. Let me show you an example. I guess I might have made a typo somewhere. Okay, I wanted to show you guys like so. These are the 34 embeddings for each node. So if I do control B, do control V, oh sorry, my mouse doesn't work. Okay, so let me just show you guys if I do this dict thing, and then I call it on this thing. This is an embedding, and then I'll call this like embedding example. And then I'll do length embedding example. So the embeddings are dimension 1536. Okay, so that's the indexing, getting the embeddings. Okay, so now we have we get a query engine for retrieval and synthesis. So let me actually show you in the diagram where this is. So the query engine does these two components. It does the retrieval, where it gets the k nearest nodes to your query, and then it does the whole synthesis, where it generates from the k nearest nodes and the query your response. Okay, so let's get back to this query engine. So to get the query engine, what do? We do just one second, I confused myself. Okay, so we can do something like this. We can do query engine, and I'll write. This is the simplest way. This is the default, but let's show a few more things. Okay, so there's a way. There's like a response mode, like how to combine the information. So I'll just do tree summarize. That's the default. And then similarity, I told you you can do top top 3, and then I'll do that. Okay, so the top 3. Okay, so this is the query engine, right? Okay, so now to get the actual we can query the query engine to get the answer, right? So we can do like query equals what are some upcoming dates Tesla investors should keep their eyes on related to Elon Musk's comp plan. By the way, here it seems like I'm cheating because I'm barely using any articles. I'm using only 11. But like in the demo where I had the AI assistant, I used way more than 11. I used thousands, and it got the answer still. So like once you have the query, then you do query engine dot query. You get a response. You can print the response by doing print response. You can do. There's also response. Okay. Okay. So then it says investors should keep eye on the upcoming shareholder meeting. So that's very useful because like if you don't keep your eye on it, and this is not like something that's in the schedule. It might be actually because it's a shareholder meeting, but like sometimes you have these dates where they're not in the schedule exactly, and being able to search your documents to find them is amazing. So so that's the response. So this is basically the RAG example. You can ask it another question. Let's just show you another question for the hell of it, saying what if we just say what are some upcoming dates this investor should keep their eyes on without Elon Musk. Let's see if it knows that it says something different. If I didn't guide it enough, basically. And again, there's so many ways to optimize and customize this. It gives you the same answer. But I am guessing if you had a lot more data, it might give you the like robotaxi event if you don't write the robotaxi unveil on August 8th if you don't write Elon Musk, or it might give you like the next earnings report or something like that. So that's why sometimes if you write the whole thing, it gives you a much more precise thing. Okay, but just to show you guys like some of the inner workings about how this works. So if you look at response, you don't just get like the response, you get response dot there's a thing called source nodes. So the source nodes, there's 3 of them, and these are the nodes that the model chose as the most the 3 closest ones, right? So if I do response dot source nodes, and then I do, let's say, the first one. Okay, so I get so if you see here, what do I have in the response? We can let's print out how it looks. We can do something like this. We can do for I node in enumerate response to source nodes, print node I, and there's also a similarity score here, and you can print node.text. Okay, So I printed like, okay, node 0, similarity score 0.857, and I printed the text. So maybe we should actually display the text as HTML to make it prettier. HTML node.text. Does this work? No, it doesn't. It doesn't work because it needs to be like one thing. Okay. Okay. Anyways, forget it. So, but like you have node 0, similarity score. Let me just hide this for now. And then it gives you the similarity scores. Okay. But what, like, how on earth did they come up with these numbers? I just want to show you guys, like, so you guys, like, know exactly how they came up. So remember what I said. I said the query gets embedded also. So, and then I said they use cosine similarity to find the similarity scores, right? And then detect the top 3. So let's show you how you can do that manually. So, like, you can actually get the embedding model by doing from llama index.core import settings. Okay, sorry, from llama index.core import settings. The AI stuff sometimes gets in your way. So then I can do query embedding equals settings.embed model. The embed model that get text embedding that embed that get text embedding query embedding. Okay, so now you get the query embedding, and just to show you it's the same dimension, it's also 1536. Okay, so you get the query embedding. Okay, so now remember I said that you do the cosine similarity with these with all the node embeddings, right? So you can let me just show you how to do it with the top nodes. So for the top nodes, remember I said there's response.source nodes, right? Response dot source nodes. Let's take the first one and then let's do what is the first one? The first one has like a node ID, right? And I'll call it top I'll call it retrieved node ID equals this, right? And then so I get this node ID, retrieve node ID. Let me show you how it looks like this, right? And then I can do I can get retrieved node embeddings, and remember I showed you previously how to get the embeddings dict of the retrieved node ID. So the AI did it right this time. Retrieved node embeddings looks it's going to be 1536 dimensional again. Okay, so now what we need is we need to calculate the cosine similarity between this embedding vector and the query embedding vector, right? So let me actually write a note. We say calculate cosine similarity between retrieved node embedding plus query embedding vector. So how are we going to do that? So sklearn has a package, so we can do from sklearn.metrics.pairwise import cosine similarity, and this is wrong. What the AI is giving us. Oh, you know what? It's right. Okay, so you can do it like this. Okay, sorry. So the cosine similarity is 0.85749, and what was our top one when we did this? 0.8749. So that's how they got it, and then so they did it, and they found the top 3, and then they plugged that in with the query into the LLM, let's say GPT-4, and they got a response, which was pretty good. So let me just give you like finally a few more notes. You can customize the embedding model and the LLM model, and I use the default, which is OpenAI's models, but there's a default OpenAI models. But if you want to customize it, you can do that, and you can also customize with like Hugging Face models and other local models. Like you can also models on Llama, like open source models and that sort of thing. So this link has a lot of examples on LLMs and embeddings and that sort of thing. So you basically have to import the settings thing from core, Llama Index.core, and then you can do .embedding model, and then if you want a different OpenAI embeddings model, you do OpenAI embedding, and then you write this. You can choose your embedding model. Same with the LLM model, Text DaVinci. You can also do GPT-4 Turbo or whatever, the embedding models you want. So that's one thing you can do. Okay, and you can also use Hugging Face embeddings. So let me show you guys how to do that. Hugging Face, of course, you can download models locally like Llama 3, my favorite model like Meta's Llama 3, and you can run it locally. But let me just show you guys, like you have to do these installs here. Embeddings, Hugging Face, Llama Index, embeddings, Hugging Face, and Llama Index, LM's Hugging Face, and you actually need Accelerate because you'll need like local GPU. This is local models. Anyways, you have to install all these things. When you do Accelerate, you have to always restart, I think. But that runs, and then similarly, you do settings.embedding model equals Hugging Face embedding model, and then you give the model name. And then for the LLM thing, it's a little bit more complicated because sometimes you have to give the more things. You have to give like more exact definitions, like the prompt and that sort of thing. So yeah. So but you still do LLM equals Hugging Face LLM. You have settings. You have your LLM and your chunk size and that sort of thing. But like settings.LLM is the big thing, and settings.embed model. Similarly to like when we wanted the custom OpenAI model. Okay, so let's just see if this runs once this completes. Hope you enjoyed this video. If you enjoyed it, again, let me preach, like, and subscribe. Sometimes I don't know which videos people like. So my original audience is like pure algo trading. But then like I'm actually very interested in AI, and I think AI is extremely important for investing. And actually my top video is on LLMs. So like the more people I get interest, the more I gauge, the more of these videos. I appreciate it a lot. Thank you so much. And this will take forever to install. So awkward silence. Probably should just stop the video, right? Okay, great. So now you can load the embedding model, and then you can load the Hugging Face LLM. Okay, great. Yeah, see, it does all the good stuff. It downloads all your models, that sort of thing, and then it gives you the LLM. Anyways, thank you guys so much. This will be on GitHub. Thank you so much. Bye bye.